Okay, so I want to say something about where the power of category theory comes from. And I think it basically comes from category theory being a sort of minimalistic language for describing composition. I mean, so many things that people think about can be put in terms of composing things together. Like when we think about moving around in space, you think, well, if I move from A to B and then B to C, I can compose those two journeys to make a bigger journey from A to C. Or if you're going to describe to someone something like, say, how to make a machine, it will be a series of instructions, a series of actions that they need to carry out. And if you compose all those actions together, you get the process of building the machine. So I think it's just something about the way that people think. We like to sort of break problems down into small chunks. And for that reason, category theory applies to so many different things we can think about. And because it's a minimalistic language, because it sort of represents this notion of composition in such a visual and simple way, we can see it being applied in all of these different systems. And that's why when you look at all these different areas of endeavour, different areas of mathematics, like set theory and logic and geometry and so on, we can see that category theory can be used to describe all of those different areas, or other areas of human thought like programming and computation and natural language. Again, we can express these things in terms of category theory. Now, there's a couple of important things that you get out of that. One is that you can see all the sort of commonality between these different structures, and you see some amazing commonality because you can see things like, for example, there's a certain viewpoint by which logic, where you're proving theorems, looks pretty much exactly the same as set theory, where you're doing functions, sending sets to other sets and so on. And it's just remarkable to see these kind of relationships between things. But what's even better is that you start to get an appreciation for what's fundamental. So you can have these ideas, like, say, in set theory, which we kind of have enshrined in mathematics as being the sort of foundations of the thing where all the other ideas come from. It turns out that actually those ideas from set theory, we can start to see with category theory that, hang on, these notions are not fundamental. They are they can be expressed in terms of category theory and generalized to lots of other categories. So for me, this is what really got me hooked on the subject, is that you start to get a wider appreciation for what kinds of things are really fundamental in mathematics. And so we then see that there are other ideas from category theory which apply all over the place. And because we're sort of working in this language which is so fundamental, everything fits together very nicely, and it's really a very satisfying thing to learn about. So that's part of the reason I think it's such a great language. Another reason is because we can deal with mathematics with the sort of large scale structures of mathematics. So category theory has been described as the mathematics of mathematics, because what you can do is you can define a kind of mathematical object, like, say, a set or something, and you can then say, well, is there a category that this object lives in naturally? And there often tends to be, and these categories are sort of infinite structures, very nice to think about, and we can then compare them with each other. And so we can say, for example, what are the similarities between set theory and topology? And we'd have one category representing what's going on in topology and another one representing what's going on in set theory, and we can just show relationships between them. And this can be done remarkably easily, considering these immense kind of structures that we're comparing. So it's really sort of like going in a helicopter very high above the landscape and being able to see all the details of the things that are going on. So what's category theory about? Well, categories. So a category is a collection of objects, and these objects we can draw as points because they're sort of atomic entities. They don't really have any structure in and of themselves, but between these objects we have arrows. So these arrows could represent relations, they could represent actions, and the core notion in category theory is that we can compose arrows to get other arrows. Just like if you go on a journey from A to B and then a journey from B to C, you can compose those to make a journey from A to C. Okay, so this is my first little category that I'm drawing, or part of it. And it has these objects A, B and C. And let's label these arrows. Let's call them F and G. So I say, again, a category is a collection of objects we can draw as points with some arrows between them. So at this point you might be thinking, well, isn't that just a network? And it's true that networks do have a lot of similarity to categories, but there's a bit more to a category than a network because we can compose these arrows. So we have these two arrows which, you know, the head of this one is the tail of this one, and that means we can compose them here to get another arrow. And we'll call this arrow, so this is the arrow you get by going along F and then going along G. It makes this big arrow, and we call this G after F. So this little circle here, we can read this as after. Okay, so I think at this point we're ready to start writing down a definition of what a category is. So it's a collection of objects and arrows between objects. So I should say at this point we can have multiple arrows between a pair of objects. We can of course have arrows going in the opposite direction. We can have arrows going from an object to itself. In fact, we must have arrows going from objects to themselves. I'll talk about those in a moment. So yes, we can have lots of arrows. But now let me write down this idea of arrow composition. Okay, so I'm writing this here as notation that just means that F is an arrow that goes from object A to object B. So it's similar to the sort of notation used, similar in meaning to the notation used over here. It's just a little bit easier for sort of linear text. So if F is an arrow from A to B and G is an arrow from B to C, then we have to have this arrow G after F, which is an arrow from A to C. So this is the core notion of arrow composition, which is really at the core of category theory. I mean, often when people draw categories, they draw these sorts of network pictures, but not all the information is really shown there, because to really know what's going on in a category, you need to know which arrow compositions make which other arrows. So we have a pair of arrows like this, you know, the destination of this one is the source of the next. And that means we can compose those arrows, and that means their composition should be another arrow in the category, an arrow that starts at A and ends at C. And we see in this picture there are two such arrows. So when we're defining the category, we'd have to say which one of these corresponds to the composition of these two. So we're getting close to having a full definition of what a category is. There's just two more properties that the structure has to satisfy in order to be a category. One of them is identity arrows. So every object has to have an arrow going from itself to itself, a special kind of arrow called an identity arrow. And so we call the identity arrow associated with object A, ID A, this is ID B, and here's ID C. And these identity arrows have the property that if we compose them with another arrow, we just get the other arrow back. So they sort of represent do-nothing operations, a bit like when you add 0 to a number, you just get that number back. So let's write that down. So for every object B, we have this identity arrow of B, which is an arrow from B to B. And it's got the property that ID B after F is F, and G after ID B equals G. Okay? So what I mean here is that if we go along this arrow and then we go around this identity, so you know we go along F and then we go along the identity arrow, that gives us as a composition just F back again. And similarly, if we go along the identity arrow first and then we go along G, then that just gives us G back. And this of course has to hold for any functions, any sort of incoming arrow, I shouldn't call them functions at the moment, any incoming arrow F, and any outgoing arrow G. Right then, so okay, final part of the definition of a category is associativity. We want this arrow composition to satisfy this extra law or extra condition called associativity. So what is it? Basically, let's say we have 3 arrows like this, F, G, and H, and we want to compose these arrows together. So I've just told you that we can compose pairs of arrows together. to get the third ones. But here we have 3. So how do we compose them? What order do we compose them together in? We could compose these 2 together and then this one, or we could compose this one and then these 2 together. And the answer is it doesn't matter, because we're assuming that arrow composition is associative. So what that boils down to is saying that if we compose H together with the thing that we get by composing G and F, so if we compose this green arrow and then this orange arrow on the right, that'll give us the same thing as if we compose this orange arrow on the left and this purple arrow on the right. So that would be so what we're basically saying, I mean, the way I'm writing this, I'm using brackets to represent that. In this case here, we're composing these 2 arrows first to get this green one, and then we're sort of composing with H after that. In this case here, we're evaluating this composition first and then we're composing with F. But I'm saying it doesn't matter which one of these you do. So essentially that just means that we can just write H after G after F. And we don't have to use these brackets because we don't have to worry about which order we're composing these pairs of arrows. And this is similar to what we have in arithmetic. In arithmetic we have, of course, 1 plus 2 plus 3 is the same thing as 1 plus 2 plus 3. Okay, so addition with whole numbers, with any numbers, is a associative operation, and we're assuming that this arrow composition is also associative. And really this is just to make category theory easier. You know, you could play around with systems where this doesn't hold. You might want to think about mathematical operations that are not associative. Can you think of one? Okay, I'll tell you one is division. So that's not always an associative thing. But anyway, that's basically the definition of a category. So let's just reiterate. A category is a collection of objects, arrows between objects, and we can compose arrows. So whenever we have 2 arrows that the source of the destination of the first is the source of the second, then we can compose them, and there'll be another arrow that's their composition that has the same source as the first one and the same destination as the last one. Every object has to have an identity arrow that has a property that if we compose any other arrow with it, we just get that other arrow back. And arrow composition has to be associative. Anything that satisfies those conditions is a category, and that's what category theory is all about. It just turns out that this type of structure is really, really useful for expressing loads of things. Okay, so now I'm going to talk about some examples of categories, and this is going to get very interesting very fast because there's some really mind-blowing kinds of infinite categories which are really fundamental to mathematics and very, very interesting. But before that, let's start with the simplest categories. So the very simplest category is shown on this blackboard behind me. It's the empty category. It has no objects and no arrows. And as fascinating an object as that is, let's look at something a bit more interesting, which is the category which just has one object and as few arrows as possible. So are we allowed to have no arrows? No, we're not, because we have to have an identity arrow for every object. So moving up slightly, we have these categories which have multiple objects, but only these identity arrows. I should call that IDA, excuse me. And then this will have an identity arrow IDB, and this will have an identity arrow IDC. So we have categories like this, and you can think about, it's a very nice exercise to see if you can draw out some of the very simplest categories which we have. So here's a sort of non-trivial one, still very simple. And we'll just have one arrow between those. And you can carry on, you can think about, okay, there's a category with two arrows. There's another one which occurs a lot. And so on. Now let's talk about a type of category which is very important in mathematics, and that's a category which has just one object but potentially many arrows. So of course it has, let's call this object A. And of course it has to have this identity arrow. And it can have other arrows as well. Okay, so potentially many other arrows going to itself. And that type of structure is very important. I'll tell you about a couple of examples of it. And it's something called a monoid. Okay, so I don't want to overload you with definitions at the beginning. We will go into what monoids are later, but I mean, I've already basically told you the definition of a monoid because I've said it's a category of one object. And basically, we have all these arrows going from the object to itself. And I've told you about how you can compose these arrows. Of course, if you compose a couple of arrows going from the object to itself, you get another arrow going from the object to itself. So you can think of these sort of self loops as elements, and you can think of there's some sort of an operation where you take a couple of elements and you get an element out, and that's encoded in the arrow composition. So an example is, in this case, let's say we call this identity element, let's call it 1, and let's just call this arrow 0. Okay, so if we imagine that the arrow composition is multiplication, then it works out quite nicely, because we have 0 times 0 is 0. So in other words, we're imagining the composition of this arrow with itself is itself. If we compose this with itself, we get that arrow again. And then this does indeed act like the identity element, because if we pre-compose it with 0, we get 0. If we post-compose it with 0, we get 0. And if we compose it with itself, we get itself. So this category where we just have one object, and we think of these two arrows as 1 and 0, and we think of composition as multiplying those. That gives us a bona fide category. I've shown that the identity element is well behaved. You can think about, does this satisfy associativity as well, which it would have to do for this to be a category, and indeed it does. So this is a nice simple idea of a category. A more useful one perhaps is this time we'll call our identity element 0, and we're going to have lots of arrows. So there's 1, and we'll have another arrow which we'll call 2, and another arrow which we'll call 3, and we can carry on. Let's say we have an arrow for every whole number, okay, every integer. So in this case, we can say that arrow composition corresponds to addition, and again we get a category. So these are all examples of things called monoids. Basically, a monoid is just where you have a load of elements, you have an operation that takes any pair of them and makes another one, and it is an associative operation, and it has a sort of identity element. So it's just what I wrote on the board before, but just applying to the arrows, going from this single object to itself, the arrows being thought of as elements. So monoids are very interesting, and they're well worth studying. Indeed, if you want to understand category theory, monoids are a kind of good place to start, because like one of the things that is kind of hard to wrap one's mind around at the beginning is this idea of composition and what type of operations you can what kind of things you can do with composition, and monoids are a great place to study that in miniature, because in monoids we can compose anything with anything, whereas in categories they're a bit more intricate, because we can only compose arrows which are head to tail. Okay. So the other example is something called a preorder. Okay, this is the other sort of, so a monoid is a great way to get your head around composition, because it's a category which just has one object but lots of arrows potentially. And the other extreme is a sort of preorder, or a preordered set it's sometimes called, and that's a kind of category that has lots of objects, but it doesn't have that many arrows. In particular, it doesn't have more than one arrow going in a particular direction between two objects. So how do we get a preordered set? Well, a nice easy way to think about it is, if we start with any directed network. Okay, so a directed network is a kind of simpler idea than a category. It's just where you have a load of dots that you can call nodes or vertices or objects, whatever you want to call them, and then you have some arrows between them. So there's an example of a directed network. It's not a category because, for example, we have an arrow from here to here and from here to here, but we don't have an arrow from there to there. So the composition is missing. We also don't have any self loops. So it's not a category, it's just a directed network. But we can turn it into a so-called pre-ordered set. I mean, we have this set of elements, nodes, if you like, and we can basically, we can turn it into a pre-ordered set. So how do we do that? Well, basically, we think about walking around on this network, and what we say is we're going to draw an arrow whenever we can walk from one element to another using these arrows. So we already have an arrow from here to here, so we don't have to draw one in, but we can indeed walk from here to here to here. So we should add an extra arrow from here to here, because that's basically, the arrows are representing the presence of paths. Similarly, we can go from here to here, and we can go from here to here. And we can also do a sort of no distance walk from an object to itself. So if you started with a directed network which didn't have any multi-edges, okay, so there wasn't any of this business where we had multiple arrows between an object and the thing that we started with, like that, none of this initially, then if we add these extra arrows to represent the possible paths, then we end up with something basically called a pre-order. I mean, usually in mathematics, and also I should say any pre-order can be created like this. If you look at the definition of a pre-ordered set, it'll be defined somewhat differently probably, but this is an equivalent definition of it. And usually you would write, so if there's an arrow from, let's say, A to C, as there is, you'd write A less than or equal to C. Okay, so now I want to talk about one of my favourite ideas in category, and it's a sort of large-scale infinite category, which is amazingly important for mathematics, and it's really a very fundamental and rather beautiful notion. It's called the category set, capital S-E-T. It's a category, and the objects in this category represent sets. So we can think of a set as a load of elements So for example, this is the set which has 1, 2 and 3. And one of the remarkable things about this category called set is that its objects, each of its objects represents a set, and we imagine that all sets are represented. So this is a pretty mind-blowing idea already. I mean, actually, it goes a bit too far, because if you start thinking about the collection of all sets, you're in paradox country, okay? Things can go a bit wrong with the logic, because that's just there's so many of these things that things can go wrong. So there is a way to set up this kind of thing rigorously. You can essentially define a sort of universe of sets which holds all of the sets which you may encounter by doing the familiar operations. and it's an immense kind of collection of different sets, and everything we do in mathematics, every set that we'd refer to is an element of that. And we can just say that each of the members of that universe, each set in that universe, is one of our objects, and those are our objects. But I'm not going to get too hung up on these foundational issues. I just want to introduce this amazing idea. So each object represents a set. So for example, this is a set holding 1, 2 and 3. And then there'll be another object over here, which is a set holding true and false. And yeah, so these are the objects. And then what are the arrows? Well, the arrows are functions. So a function, let's say, we'll call this set capital A and this one capital B. A function is something that sends each element in a function from A to B is something that sends each element in A to an element in B. So there's a function f from A to B, and there's various other ones. So our arrows are functions, and all functions between these sets are arrows in this category. So this category set has objects as sets and arrows as functions. Okay, so I still need to tell you how we can compose these functions. How can we compose these arrows together? I mean, remember in the definition of a category, if you have two arrows and the head of one is the tail of the next, then you can compose them, so their composition must exist. So we have to define how we're going to compose these arrows together. So let's say we have another set over here. Let's say this has elements little a, little b, little c, and little d. And say we have another function, g. So how do we compose f and g? That's something that I'm going to have to define. I mean, basically it's pretty straightforward. We just go along an arrow f, see what element we're at, and then follow the arrow out of that element with g and see where it ends up in this set, capital C. So the composition of these two arrows, these two functions, looks like this. So 2 goes to f, goes to b, so in the composition 2 just goes straight to b. 3 goes to f, goes to b, so in the composition 3 just goes straight to b. So this here is the composition, and we can call it g after f. Okay, so let me just introduce a bit more sort of background for you to think about these functions. One view of a function is it's something like a black box, and if we feed in an element, so this is this green function from A to B. If we feed in an element from A, then we get out an element from B. And the way that we'd write this normally is f of the input is equal to the output. Okay, so this is basically a way we'd sort of write about these things. And how about the composition? How do we define that? Well, the way it would be defined is we'd say that g after f is a function, and if it's operating on an element X, what we get is what we get if we apply G to what we get if we apply F to X. So if we start with 1, we apply F to it, we get T, then we apply G to it, we get A. Therefore, G after F of 1 is equal to little a. Okay, so we can compose our arrows. We have to, or we wish to prove that this, so we want to now show that this is actually a category. Okay, so this means that this arrow composition has to satisfy the different laws of the category. And remember, there's 2 of them that we have to satisfy. One is that we have to have these identity arrows, which just are sort of arrows which go from objects to themselves. So in our case, these objects are sets. And so we need some kind of function that goes from a set to itself. And it sort of has to be like a do nothing kind of function, because it has to have the property that if we compose it with other functions, we just get the other function back. And there are such functions, and they're basically called identity functions or identity maps. So it's just a function which sends every element to itself. And I think quite clearly there's going to be a function like that for every set. So that's good. We have our identity arrows. The other thing we need is associativity. So we need to show that for these composable functions, we have this. Anyhow, remember though, so I've drawn some of the sort of goings on in this category set up here, but this isn't really how we'd represent it in category theory, because remember I told you that in category theory our objects, which in this case are representing sets, well, our objects are just thought of as sort of atomic things. They don't really have any internal structure. So this is a bit strange. Where has all our information gone? How do we know how many elements there are in these sets? So what do we know in category theory? Well, we have the objects that represent the sets, and we have these arrows between them which represent the functions. And so haven't we just lost some information here? Because we're no longer depicting the elements within the sets. And the answer, which is quite remarkable, is no. We haven't really lost any information. It turns out that we can recover the information about these particular sets, you know, how many elements they have in them. We can recover that information just by having this category. So in this category here, we have the objects and we have the arrows, and we also know which arrows compose together to make other arrows. And it's a remarkable fact that in fact that's enough for us to be able to identify particular sets and particular mappings and so on. So how does that work? I'm going to talk a little bit about that in a bit. Let me just talk something more about why this category set is so useful in another way. And that is the sort of application that it has in programming, in particular in functional programming. So there's various different ways to do programming. One of them is by writing loops and mutating values and so on. There's another very elegant way to do computer programming, which is functional computer programming. And in that kind of scenario, what you're doing, what your code is basically, is a load of functions which you compose together, and you end up getting an output at the end and you're finished. So this is a very nice idea, and it's closely related to this category set. So just to give you a very small flavour of this relationship and what functional programming is about, let's say you have a programming problem, which is that you want to write a code which is going to tell you if a particular word has 3 or less letters. So here's how you can think about that in this context. So you could say, okay, I have a set of words and then I also have this set here, which is the set of all non-negative whole numbers, so 0, 1, 2, 3, 4 and so on. And we'll also have this set here, which just has 2 elements called true and false. So how are we going to write this program? Well, we're going to use function composition. Okay, so let's make a function which goes from the set of words to the set of non-negative whole numbers, and we're going to call this function length. And it's going to send a particular word to the numbers of letters in that word. So it would send cat to 3, for example. Now let's have another function which goes from these non-negative whole numbers to true and false, and let's call that function less than or equal to 3. Okay, so the way this function works is that if your number is less than or equal to 3, then it's sent to true. Otherwise, it's sent to false. Okay? And so now if we compose these two functions together, we'll get another function which basically sends a word to true if it has less than or equal to 3 letters. Otherwise, it sends it to false. Okay, so that's something about how you can use how function composition is used in functional programming. And this is quite remarkable because it basically boils down to saying that when you're doing functional programming, you're sort of just walking around on this category set. I mean, there are details. It might not be exactly the same because of types and infinite procedures and so on. But I mean, basically, this gives you a very nice idea of what's going on in functional programming. And this is one of the reasons that category theory is often of interest to people who are doing that. Okay, so now I want to start to substantiate this claim I was making, which is that if we're looking at this category set, and if we're taking a categorical viewpoint on it, so we're only looking at the objects as sort of points, and we have these arrows between them, then I claim that we can actually identify the different sets which are involved and which functions these different arrows represent and so on. So how can we do that? Well, the key is a general definition of something called a final object. So a final object, F, is an object such that for any object A, there's a unique arrow, just one arrow, from this object A to F. Okay, so if these are our objects in our category, and this is a final object, then there's just going to be one arrow from every object to this one, and just one arrow from this object to itself, the identity arrow. Okay, so why is this important for understanding about this category set? Well, because there's a particular object in this category set, a particular set if you like, which is a final object of this category. And maybe you would like to pause the video and think about what kind of set would represent a final object in the category set, because it's really the key to understanding this issue. Well, it turns out that if we just pick a set which just has one element in it, then that object that corresponds to that set is actually a final object. And it's quite easy to see why. If we have another set, so this would be represented by another object in our category, and how many arrows are there from this object to this object? How many functions are there from this set to this set? Well, there's just one, just the function which kind of collapses all of the elements of this set on the left into this set on the right. It's kind of like a black hole. So that's great, because that means that just by looking at the objects and the arrows, we can identify the singleton set, the object representing the singleton set in the category, without having to actually look inside of these objects at, you know, what elements they have and what they're supposed to represent. We can just look at the arrows and determine where the singleton, which object represents the singleton sets. Now, that's not all. It's very fruitful to then ask, well, what are the arrows going from this singleton, this object representing the singleton set, to other objects? So what functions are there going from this set here to this set here? Well, there are three of them. There's one like that, one like that, and one like that. So this is really quite remarkable, because we can then identify a set with, we can identify an object representing a set with three elements in this category as something that has three arrows incoming upon it from the singleton set. So, I mean, this is how this picture looks like when we're allowed to actually look at the elements in these sets. But from a categorical viewpoint, we would just see something more like this. We have this sort of final object here. Final objects are also called terminal objects in categories. But anyway, we have this final object here. And of course, there's just one arrow from this other object to it. But there are three arrows going from this final object to this object on the left here. And so by just looking at the arrows, we can then say, hey, this must represent a set which has 3 elements. And moreover, each of the elements in this set corresponds to a particular arrow. So we no longer have to talk about the elements of a set. We can just talk about the arrows coming from this final object into them. And this really gives us a way to sort of generalize lots of the things that we talk about in set theory. And there are various other ways to generalize things as well. Just to make sure I've got this idea clear, I mean, let's say we have another set over here, true and false. How could we identify this, the object representing this set in our category set? Well, we just again look at what are the arrows coming out of this final object here. And we see there are 2 of them. So when we're just looking in our category set and we're not allowed to sort of peep inside these objects and see what they represent, we can still identify this as a 2-element set because there's just going to be 2 arrows coming out of this final object into it. So yeah, and there's various other ideas from set theory that you can generalize in a similar kind of way. For example, if we have 2 sets like this one here and this one here, we can form another set which has pairs, 1 element from here and 1 element from here. This is the so-called Cartesian product of this set here and this set here. It's another set. And I always used to think that such a kind of product of 2 sets was a fundamental idea in mathematics. Turns out it's not. Turns out this idea can be expressed in terms of category theory and generalized to lots of other categories as well. Not all categories have final objects, not all categories can have this kind of notion defined in them, but many important ones can. And so we're going to get some understanding of what's fundamental in mathematics from a kind of new, more global perspective.